next session. Okay, so in the introduction to queue, like a stack, the queue is also a data structure. Okay, in stack we will perform the addition and deletion operation at only one end, but in queue we will do it in two ends, that is front and rear. Here we will maintain two pointers. One pointer will be pointing to the front of the queue and another pointer will be pointing to the rear of the queue. Whenever a new element is added, it will be added at the end of the queue. Okay, and whenever we are removing an element, it will be removed from the front of the queue. So this is what the basic concept of a queue. Okay, it is like any ordinary queue. It's a means a bank queue or wherever the fees queue line. Okay, so in any real life queue, normally we will add at the end of the queue, and the person who is standing in the first, that is in the front, he will get the service and he will be removed from the queue. The same queue here we can implement. So this is the queue data structure. A queue is a linear list in which data can be inserted at one end called rear, okay, and deleted from the other end. It is called as a front. And this data structure is called as a first in, first out. Means whoever standing in the queue first, he will get the service first. First in and first out. He will come out of the queue first. So this is before structure. Okay, and the basic queue operations are in queue, DQ, queue front, and queue rear. In queue means adding an element into the queue. DQ means removing an element from the queue, and queue front means checking what is the element in the front. Okay, front of the queue. Queue rear means checking what is the value in the rear of the queue. Okay, who is standing at the last? Who is standing at the first? Checking this is queue front and queue rear. Okay, and the in queue operation. Okay, so we'll directly go to the algorithm. Okay, here the operations explained here. Okay, so in detailed pictures. Okay, now the linked list implementation of a queue. How we implemented the queue using, sorry, stack using linked list. The same way here we can implement the queue also using linked list. Okay, here also we need to maintain two structures. One is the data node structure and another one is the head structure. Okay, in stack the head structure contains count, the number of nodes, and the top pointer. Okay, and as we already discussed, the queue needs two pointers. Okay, it should point to the first node of a queue and also it should point to the last node of the queue. Okay, so we need two pointers. So here in this queue linked list implementation, okay, the head structure, we need to declare two pointers, front pointer and a rear pointer. Okay, just to check the example given, sorry, the picture given here. Okay, so here the head node contain, the front pointer is pointing to the first node. Okay, that is plum. The rear pointer pointing to the last node, that is fig. Okay, so this is on the linked list implementation. Okay, head structure pointing to the first node of the queue and also last node of the queue. Okay, because if you want to insert an element into the queue, you should know who is standing last. Then only after him you can insert the new data. Okay, suppose if you want to remove an element, you should know who is standing first. That person must be removed. Okay, then the next person becomes the first person. Okay, so for that we need to know the first data or first element in the queue. So for this purpose, we need two pointers, front and rear pointers. Okay, see here, head structure and the data node. It's a physical illustration. Okay, so the pictures given here, and the left side the structure, C implementation structure. Okay, two structure we are going to use. One is a node structure. It contains data and the next pointer, self-referential pointer. Okay, and the head structure. Okay, head structure contains count, the number of elements in the queue, and also the front pointer and the rear pointer. Okay, this will be pointing to the first node and also the last node of a queue. Okay, so this is these two structures we need to implement the queue using linked list concept. Now the queue algorithms. So these are the 8 algorithms we are going to discuss in queue. First is creating a queue, and second is the enqueue operation. Next is the dequeue operation, and then retrieving operation. So retrieving means retrieving the first node and retrieving the last node data, and empty queue. Okay, then full queue, whether the queue is full or not. Okay. Just 1 minute. 1 minute, please. Okay. Now, yeah, let us discuss about the first queue, first algorithm, that is create queue. Okay. So in create queue, it means whatever algorithm we are here we are going to discuss, create queue, enqueue, dequeue. So all these algorithms, the steps are more or less similar to the stack algorithm. So if you are understanding the stack, create stack algorithm clearly, then here create queue algorithm also more or less same. There you can understand push and pop operation, that implementation clearly. The same here we are going to implement in enqueue and dequeue operations. Let us start the first algorithm, create queue. Okay, so this is the algorithm for create queue. To create a queue operation, okay, first what we need to do is we need to create the head structure. Okay, allocate memory for the head structure, then set the queue front and queue rear pointers to null, and the count operation, count value to 0. Okay, so this is what the create queue operation, create queue algorithm. Okay, it's equivalent to C implementation. See here, we are passing the queue pointer and allocating memory for the queue pointer. Suppose it returns null, means the error in the memory allocation. Okay, so we are returning 0. Suppose if it is not null, means the memory allocated successfully. So in that memory, for count value we are assigning 0. For front and rear we are assigning null, null. Okay, and finally we are returning 1. Okay, 1 means the create queue operation is successful. Okay, so this is what create queue C implementation. Now enqueue operation. Okay, so enqueue operation means it is the add operation. Okay, we created a queue. In the queue, the first element we are going to insert. Okay, so here we face two conditions. What are the two conditions? Means inserting the first element in the queue, okay, or inserting an element with the queue which is already having some values. Okay, so these are the two scenarios we will face when we try to insert value into the queue. Okay, so the first condition, inserting into an empty queue. Suppose if you are going to insert the first data into the queue, means the front and the rear pointers both must be pointing to the same node. Okay, if there is only one element in a queue, front also that data and the rear also there is a data. Okay, suppose if you are the only one person standing in a queue, you are the first person and you are the last person. Okay, so this is what the meaning. Okay, so the front and rear pointers must point to the same new node. Okay, we need to create a new node, and that node is the first node in a queue, means we should assign the front pointer to point to the new node, and also we should assign the rear pointer to point to the new. Okay, so this is what the first case. What is the second case? The second case is adding at the end of the list or adding at the rear pointer. Okay, so here in the second case, if you are taking, the queue already contains one data called the plum. Okay, now we are creating a new node kiwi. Okay, so the new pointer contains the kiwi data. Now whatever the node pointed by rear, okay, its next should point to the new node, and then the rear should point to the new node. Okay, the plums next, it should point to kiwi, and the kiwi must be pointed by the rear. Okay, see, after changes the queue will look like this. So front is plum and the rear is kiwi. Okay, so this is the scenario after inserting the new data. Okay, now these two cases are how we are solving in algorithm. Let us check it. See here, when we algorithm, if queue is full, error statement, okay, return false, otherwise allocate a new node. Okay, once the memory is allocated, move the data to the new node. Whatever the parameter data we are getting, pass the data to the new node data. Then new nodes next, initialize the new node next value, next pointer to null initially. Okay, and check if the queue is empty. Queue is empty means front and rear value will be null. Okay, if front and rear value is null, means there is no data in the queue. So whatever the data now we are going to insert, that is the first element in the queue. So set the queue front to address the new pointer. Okay, normally we will add only at the end of the queue. So we will assign the rear pointer to point to the new node. Okay, since this is the first node we are going to insert, okay, the front also should point to the new node. That is what the true part of the if condition. Suppose if the queue is empty, set queue front to address of the new node. Else set next pointer of the rear node to new node address. Okay, so rear should point to the new node. Okay, and the queue's rear pointer, it should point to the address of the new node. Okay, see here. Already whatever the address rear is pointing, okay, whatever the node it is pointing to, its nodes next should point to the new node. That is, plum should point to the new node. See, plum should point to kiwi modified, and finally rear should point to the new node. Rear is pointing to new node. So that is what we are explaining here. Q, rear should point to the new node. Okay, and incrementing the q count, return true. Now the NQ operation is successful. Okay, NQ operation is successful. Now we discussed about two algorithms. There is a create queue and NQ operation. What is NQ operation? Adding a new element into the queue. Okay, in adding a new element into the queue, we have two cases. The first case is if the queue is empty and we are going to insert the first value. The second case is queue already has some data and we are adding the value at the rear of the queue. So these are all the two cases. So if you're taking the algorithm, the sixth point, this if condition handles the first case. Okay, and else part and the ninth point, it handles the second case. Okay, now the C implementation, let us check. See here in queue, we are getting queue of the pointer to the queue and the data to be inserted. We are creating a new memory for the new node, and if the no memory allocated means error. Otherwise, we are initializing the new node data to the parameter data, and the new node next as a null. This is initial. After that, we are checking empty queue. So this is a function. We already created this empty queue function in our algorithm itself. So we are checking whether it is a empty queue. If empty queue means the front also should point to the new node. Else, whatever the last node is pointing to, that node's next must be new node. So queue rear, it is pointing to one node. Its next should be new node. And finally, the rear pointer should point to the new node. Queue rear equal to new node, and increment the count operation. Okay, see here, once again I'll explain. Whatever the node rear is pointing to plum. Plum's next must be kiwi. Okay, rear node is pointing to this. Okay, and its next is kiwi. And finally, rear should point to kiwi. Rear is pointing to kiwi. That's it. Over. Okay. Now, the C implementation we discussed for NQ operation. The same way, let us discuss for DQ operation. Only NQ operation and DQ operation is a little bit difficult. The next is a Q front and Q rear. Simply reading the value of Q front and reading the value of Q rear. That's it. Now, what is DQ operation? DQ is more or less similar to the top operation in the stack. That is removing a data or removing a value from the queue. Okay. Here, first we should ensure that the queue contains data. Okay, the queue contains data. If the queue is empty, we cannot read any value from the queue. Okay, and whenever we are performing the DQ operation, we must reduce the count operation. Okay, count minus we should give. Okay, so the next this is the picture illustrating the queue operation. Okay, so this is a queue initially. Okay, and here also in the DQ operation also we have two cases. What are the two cases? Means deleting the last value in the queue or deleting an item at the front of the queue. Okay, just one more minute, please wait. Okay, so in delete DQ operation also we have two cases. That is deleting the last node from the queue or deleting the deleting the only one node from the queue or deleting the node or the value in the front operation. So the first picture illustrates the first case. Okay, here the head node. Okay, both front and rear both are pointing to the one node plum. Okay, the plum is the only one node available in queue. Now the front and rear both are pointing to same node and the count value is 1. If this is the case, the queue contains only one element. Okay, so we should mark the rear as a null. Okay, after deleting this, the rear should point to the null because we always delete value from the front. So after deleting this node, rear will point to nothing. So make the rear to point to null. Then delete the plum. Okay. And second case, delete item at the front of the queue. Okay. Now the front is pointing to plum. We need to delete this plum node. So before that, what we need to do means we should create a temporary pointer and make it to point to plum. That is the first. Next, whatever the value pointed by front, that is plum. Okay, the front must point to plum's next. Okay, plum's next is a kiwi. Now front should point to kiwi. So front equal to front next. Okay, whatever the value pointed by the front, it's next. Okay, so that should, this address, kiwi's address must be stored in the front. See here in the after changes, front is pointing to kiwi and the node is recycled. Okay, so this is the case 2. Okay, so in delete operation also, that is dequeue operation also, we have 2 cases. What are the 2 cases means? Only one node. Okay, queue with only one node, how to delete, and queue with more than one node, how to delete it. These are all the 2 cases. Now let us check the algorithm. See here, if queue is empty, return false. This is default case. Okay, if there is no queue, we cannot perform the dequeue operation. Now move front data to item. So we are getting a item as a reference variable. Whatever the data item we are going to delete, that we need to store it in this item. So item equal to front data. Now if only one node in the queue, if the queue contains only one node, set queue rear to null. Okay, if you are checking this if condition, it is just opposite in the enqueue. There, if the queue is empty, we pointed the front to point to the new node. Here, we are making the rear to point to null. Okay, so after deleting the only one node, rear should point to null. So we are setting rear to point to null. And then queue front to queue front next. See here, queue's front, it should point to queue's front, that is plum's next, kiwi. So front must point to kiwi. So that is what the 6th point. Queue front equal to queue front next. Okay, whatever the queue front is pointing, it's next, whatever it is contains, that you are assigning to queue front and decrementing the queue count. So this is the dequeue algorithm. Now let us see the implementation. Okay, so here we are passing queue and data as reference and checking whether the queue is empty or not. Then data equal to queue front data, because we are going to delete the front node from the queue, and its data we are moving to the data reference, and the temporary node equal to queue front. Okay, so we need to free the memory allocated to the first node in the queue. So a temporary pointer must point to the queue front, and we are checking queue front equal to queue rear. So queue front and queue rear both are pointing same, means there is only one node, and the queue count equal to 1. So queue count equal to 1, only one node, and both are pointing to the same node. If that is the case, means the rear must point to null. Okay, so this is the if condition handles the first case. There is only one node in the queue, and that node we are deleting. Okay, so that is handled by the if condition. Next, queue front equal to queue front next. Okay, so queue front must point to the node in the front. Okay, it's next. Whatever the node it is pointing, its address we need to store it in the front. Finally, free the memory allocated and decrement the queue counter. Okay, decrement the queue counter. Okay, decrement the queue counter. Now, the front and the rear operation is simply reading the values in the front and value in the rear. Now let us run the program and check the output. Then we will come to the other algorithms. Now this is a queue operation. So 2 structures we created: data structure, data node structure, and queue head structure. Okay, it contains front and rear pointers. Okay, front pointer will be pointing to the first node, and the rear pointer will be pointing to the last node in the queue. Okay, now create queue. We are allocating memory for the queue and initializing front and rear to null and count to 0. Enqueue operation, the same implementation that we discussed in the presentation. Enqueue and dequeue operation. Now let us check it. See here, I am inserting the values of 10, again 20, again 30, again 40. Now let us check how many values are there. 5. So count is 4. Totally 4 elements I have inserted. Okay. Now what will be the value in queue front? Any idea?
10.
10, sir.
Yes.
10.
Yes. 10 is Q front, and the rear value.
40.
40.
Yes, correct. Let us check it. See here, Q front is 10. Okay, and 4. Q rear is 40. Okay. Now let us exit. Okay. Let us check the remaining Q front and Q rear algorithm. After that, we'll come back to the execution of the program. Okay. Now we discussed about the three algorithms. That is creating a queue, NQ operation, and DQ operation. NQ means adding a value into the queue, and the DQ means removing the value from the queue. NQ always it will happen at the rear of the queue, end of the queue. Okay, and DQ it always happens in the front of the queue. Okay, in the beginning of the queue. Okay, these are all these three operations we discussed so far. Now the next operation is a retrieval. Okay, reading the value from the queue. Like stack, here in queue also traversing the queue is not allowed. It is not a proper operation. Okay, you can read only two data from a queue. Okay, you can check who is standing in the front of the queue and who is standing at the end of the queue. Okay, remaining you cannot navigate to each and every element of the queue and read its value. Okay, it is not allowed. It is not queue operation. Okay, you can check what is the value in the front and you can check what is the value at the rear. That's it. Okay, so now the queue front is simply reading, like it's equal to the stack top. Okay, so queue front means reading the value at the front of the queue. Okay, so this is the algorithm. If the queue is empty, return false. Okay, otherwise move the data in the front to the data out, return true. Okay, we are passing a reference data out. Whatever the value at the front of the queue, that you are copying to the data out. Okay, the same way, the third point. Okay, what changes we need to make in the third line to make it as a queue rear? In the third line of the algorithm, we need two changes. What change we need to make? Any idea? So this algorithm is a queue front, reading the value in the front node. Okay, we need to convert this algorithm into queue rear, reading the value at the rear of the queue. Okay, so in the same algorithm, what change I have to make? Any idea?
Data at rear.
Correct. Move the data at the rear of the queue to the data out. Okay, so in the head pointer we have front pointer and also we have rear pointer. Okay, queue front means use the front pointer to read the data. Queue rear means use the rear pointer to read the data. That's it. Now let us see the implementation. See here, queue front and queue rear functions. Okay, if the queue is empty means we cannot read a value. Otherwise, data equal to queue front data. Okay, so queue front means it is pointing to one data node, and in the data node, what is the data available that you are copying. Okay, queue rear means this queue rear pointing to one data node, and in the data node, what is the data available that you are copying to the data reference. Okay, queue front and queue rear. Okay, now let us go to the code. See here, queue front. So if the queue is empty, you cannot read any value. Otherwise, queue front data and rear. Okay, queue rear data. So this is how we are reading the value from the front and rear of the queue. Okay. Now the next is the empty queue. Empty queue, if count equal to 0 or queue is pointing to null, queue front and queue rear is pointing to null, it is a empty. We can say it is empty queue. Okay, you can use any one of the way. Okay, all the ways are correct. And this is the port to check empty queue. Okay, if the queue is null or queue front and queue rear both are equal to null means queue is empty. So return 1 is empty queue. Okay, return true. Otherwise return false. And full queue. Okay, like a stack what we discussed. It is difficult to check whether a stack is full or not or queue is full or not in dynamic memory allocation concept. If you are implementing the stack or queue using array, you can fix the array size. How many elements we can store maximum, 100 elements, 10 elements. In such case, we can say a stack is full or queue is full. Okay, in dynamic memory allocation concept, it is difficult to say whether a stack is full or queue is full. Okay, because the operating system will allocate certain amount of memory for each program. We don't know how much amount of memory remains. If we know, then only it's possible to calculate whether we have sufficient memory to create further nodes and everything. Okay, and nowadays we have maximum capable of memory available. There is a RAM capacity is available, 4 GB RAM, 8 GB RAM, 16 GB RAM. These machines are available nowadays in most of your laptops also. Nowadays it will contain minimum 4 GB RAM and normally 8 GB RAM. Okay, so and in particular C is not giving any option to check how much memory available for the given program. So it is difficult to implement the full queue. So we are reading only the algorithm. If memory not available, return true, otherwise return false. That's it. No implementation for to check whether a queue is full or not. Okay, and count, simply returning the count. Okay, as I already told, we should not write a logic like iterating using a while loop, visiting each and every node of the queue and incrementing the count variable and returning it. It is not proper way of uh, getting the count value. Okay, if you have a head node structure separately, okay, in head node you have count variable means then whenever we are performing NQ and DQ operation, count must be incremented, decremented. Then that count variable can be used to implement this algorithm. Okay, suppose if they are asking to write queue count algorithm, don't write for loop or while loop. Write the data structure means write the structure. Define the structure for the data node and head node, and below that write this algorithm. This is sufficient. Okay, don't write algorithm using for loop or while loop to check the number of nodes in a queue or number of nodes in a stack, because that is not a valid operation of a stack or queue. Okay, please don't do that. So simply, since we have a count variable in our head structure, we are simply returning it. Okay, that's it. Okay, and this is the destroy queue algorithm. Destroy linked list, we already discussed it. The same way here, you can delete the node from the front. Okay, by repeatedly calling the delete operation or dequeue operation. Finally, you can delete all the nodes from the queue. Okay, all the nodes from the queue. So this is the queue implementation. Okay, implementing queue using linked list. Okay, so in today's session, we discussed about the introduction to queue. Okay, so queue is also used in many applications. One application we are going to discuss is segregating the data. Suppose if you are getting n number of data continuously, and based on certain condition, if you want to segregate the separate the data, okay, though all the data less than 100 in one queue, all the data from 100 to 500 in another queue, all the data above 500 in another queue. So segregating data. So for that purpose, you can use queue. Okay. Apart from that, the tree conversion process that we will study in our third unit. That time also in the tree conversion process also we will use queue operations. Okay, and the application segregating data application and the implementation of a stack and queue using arrays concept. So this we will discuss in our later classes. Okay, so if you have any doubt in today's class, please post your doubt. And one more thing is, mostly this week exam will not be there. Next week, Tuesday, Wednesday, or Tuesday, Thursday exam.